Our galaxy is about to collide. Right now, as you're watching this video, the Milky Way is speeding toward another massive galaxy called Andromeda.
And it is rushing toward the Milky Way at around 110 kilometers per second, or nearly 400,000 kilometers per hour.
But don't worry, this isn't happening anytime soon. The collision won't begin for about 4.5 billion years, meaning humanity has nothing to fear. Despite containing hundreds of billions of stars, almost no stars will actually collide. That's because the space between stars is unimaginably vast. But how can scientists predict an event billions of years into the future? They do it by combining decades of observations with advanced computer simulations. The blue shift of the Andromeda Galaxy reveals that it is moving toward the Milky Way, while precise measurements of both galaxies' motion, speed, and gravity provide the data needed to calculate their future paths. Using this real observational data, scientists run advanced simulations that model how the galaxies will evolve over billions of years. Time and again, these simulations predict the same remarkable outcome. The Milky Way and Andromeda are destined to collide and eventually merge into a single giant galaxy. Imagine traveling through the universe and discovering a place where time itself begins to slow down. A place where 1 hour for you could mean years passing on Earth. This is not science fiction. This is one of the strangest predictions of Albert Einstein's theory of relativity. And the place where this happens is near one of the most terrifying objects in the universe: a black hole. According to Einstein's theory, gravity doesn't just pull objects. Gravity bends the fabric of space and time. The stronger the gravity, the slower time moves. A black hole is born when a massive star reaches the end of its life and collapses under its own enormous gravity. The collapse is so powerful that it creates a region where gravity becomes unbelievably strong, so strong that even light cannot escape. This invisible boundary is called the event horizon, the point of no return. But the most mind-bending thing about black holes is not just their ability to trap light, it is their ability to control time itself. Redshift occurs when light from an object moving away from us gets stretched toward the red end of the spectrum. It helps scientists measure the expansion of the universe, track the movement of galaxies, and study the effects of extreme gravity near objects like black holes. Imagine two astronauts. One stays far away from a black hole. The other travels dangerously close to it. For the astronaut near the black hole, everything feels normal. Their heartbeat continues, their clock keeps ticking, every second feels like a normal second. But for the astronaut watching from far away, time is moving differently. The clock near the black hole appears to slow down. Seconds become longer, minutes stretch into hours. This idea was famously shown in the movie Interstellar, where astronauts visit a planet close to a massive black hole called Gargantua. While the movie used creative storytelling, the science behind time dilation is based on a real effect predicted by Einstein. The closer you get to an extremely massive object, the more dramatically time can slow down.